But enough of theoretical and intuitive interpretations. Let's get to coding. First of all, let's just remind us what is a recursive function. A recursive function calls itself and needs simple base case and some recursive calls that advance towards it. Okay, these two things are very closely tied to the mathematical induction principle, and that is why I told you about it. And thinking about recursive code as an expression of that principle sometimes helps think about how it works. Recursion is a bit of a different programming technique that for some people is very natural, and for some people is a little bit hard to grasp. And I have found out that thinking about induction sometimes helps. Recursion is a very compact way of doing code, as you will see in a second. And it's sometimes very convenient too. The code is short, it's easy to read if you're used to recursion, and we will see some very well-used algorithms in the last session of the course, merge sort and quicksort, which use it in its most common form. In some areas like backtracking, it's also the go-to technique. In some other cases, it's a way to do compact code that's not that fast, and we will see some examples here. Okay, an interesting technique anyway. As I said, let's get coding. First, we want to do a code that computes the sum of the first n integers in honor of Gauss and the property that we saw for the computation of precisely that, the sum of the first n integers. Okay, we know the formula, we could just code the formula, but we are going to do it with some recursive programming. Let's start by just defining our function. Okay, so we will call it sum first n in a display of creativity, and it will have a parameter n, okay, which will show us the number that we are at every moment computing the sum up to. Okay, we need base case and a recursive case. Let's start with the former. How do we advance towards the solution? Well, when we want to compute the sum of the first 100 numbers, first we will think about computing the sum of the 99 first numbers. Okay, and if I have the sum of the 99 first numbers to use the result of that, I'm going to believe that that gives me the proper result. I'm going to trust my induction property. Okay, so if I trust that this is going to give me the proper result, then to complete the sum of the first n numbers, because this already contains the sum of the n minus 1 numbers, it's going to give me it's going to give the sum of the n minus 1 first n numbers to me. Then to complete this, to make the sum of the first n numbers, I just need to add n. So using the principle of induction, the principle of recursion in this case, I just call my function for the first n minus 1 numbers. I'm doing what I said I needed to do. I'm decreasing the parameter of the function. Okay, and then to use the result of this to build the result that I'm looking for in this call, which is the sum of the first n numbers, I just add n. Combine the result of the recursive calls with my current parameters to get the correct result. Okay, so that looks good. Let's see if it works. I'm going to sum the first 5 numbers, but hey, I got an error. What happened? Recursion error. Python is telling me that it's skipping frames because everything, and it's telling me that maximum recursion depth exceeded. Okay, so Python has many controls in place to make sure that the programmer is not doing something stupid, which I was doing at this moment, as you will see in a second. So my function looks like this. Okay, some of you might be saying, hey, this has a recursive call. This function calls itself and the parameters decrease, but you didn't write down a base case, and you would be totally right. What happened here? Well, first we call the function sum first n of 5. And because of this line, here we called sum first n of 4. And because of the same line, okay, we started with sum first n of 5, and then came here and called sum first n of 4, and then entered this with n equals 4, and came here and called it with n minus 1, which is 3, and came here, sum first n of 2, and so on and so forth. Okay, started with 5, 4, 3, 2, 1. And I have indented this so that you see that we are deeper and deeper and deeper into the calls of the recursion tree. And when I get to sum first n of 1, what do? Well, I go on, because I don't have any base case, and I keep considering sum first n of 0, n of minus 1, and minus 2, and so on and so forth. Okay, and this would go on forever. This would never stop. I would fall into an endless bit of recursive calls. Only Python doesn't let me, and after a while it tells me it has had enough and said maximum recursion depth exceeded. This is a parameter that you can actually configure, but it's telling me it's going down, I think up to 200, and saying, hey, this thing is not going anywhere, okay, and stopping me. What was the problem here? Well, I did not have a base case. Okay, I want to add all the numbers, but from 1. I want to add all the natural numbers, so I need to add a base case, and let's do it here. If n equals 1, then what's the sum of all the natural numbers from 1 up to 1? Well, that's 1 plus nothing else, so it's 1. So if n equals 1, I will return 1, and that's my base case. That's a little bit more complicated than I had, but not by much. So now my function does this. If n is 1, it returns 1. And if n is not 1, it returns n plus the result of a recursive call. Okay? Does that work? Well, yes, it does. For example, let's start with 100 numbers, which should give 50-50. So 5050. Yes. This is what Gauss is supposed to have answered, and then he was supposed to have been told to do it to 1,000, which would give 500,500. Okay, and we can use it with any number that we want, and you can also see that this works pretty fast. Okay. Let's follow the trace of execution here again. First, if we do it for 5, for example, we called the function with parameter 5. Went here and then called it with parameter 4, 3, 2, 1. And when we got 1 to 1, instead of messing up, we returned 1. Okay? Then we used the recursive call to complete the correct answer with this result that we had got. So because we were in the call with parameter n equals 2, we knew that here we had to return n, so 2 plus this result, 2 plus 1. Okay, so sum first n of 2 is 2 plus 1, which is 3. And then we added 3 to it, so to 3 to complete the sum first n of 3, so we would get 6. And then we added 4 to it to get the sum first n of 4, which would make 10. And then we added 5, which gave us the final 15 result that we could see here. Okay, so here we have our first recursive code. Recursive call, diminishing parameters, base case, and everything works fine. Okay, here you can see the tree of recursive calls and how the result of the recursive calls, once reached the base case, helps to build the solution for every call. Okay, it's important that the code advances towards the base case. If I made a mistake here and wrote n instead of n-1, then I would just keep calling the same function. So first n of 5, 5, 5, 5, and I would also end up with an infinite loop that Python would have to bail me out of. Okay, so I need recursive case with a recursive call. I need the parameters to diminish to move towards a base case that I also need, and then I need a return. And if I have all of those things, then I have a recursive function that works fine. This was our first example of recursive function. We could have computed the sum of the first n numbers with a simple loop, but I think this is even more compact if you understand what recursivity is. Let's just say a quick word about the complexity of these algorithms, of this particular algorithm. The complexity of this algorithm is of the recursive algorithm to compute the sum of the first n numbers if linear is O of n. Why? Well, because of this. See, we start at n, and then we have one recursive call for each number from 1 to n. Okay, and then we have another place where we use the result of that recursive call, but we also have one for each number from 1 to n. So basically, we do something. We do the call and then the combination. We do these things once for every number from 1 to n. So the whole number of times that this is called is proportional to n. So the complexity of this is linear. First, recursive algorithm, base case, recursive case with diminishing parameters, and it was linear.